Hi, my name is John Paul, fourth year student at CCT.
And I'm Halima, also a fourth-year student at CCT. In this video, we're going to be talking about a project that analyzes the methods of intelligent spam filtering techniques in the SMS text paradigm, in the context of mobile text message spam. The unique characteristics of the SMS contexts are indicative of the fact that all approaches may not be equally effective or efficient. This paper compares some of the popular spam filtering techniques on a publicly available SMS spam corpus to identify the methods that work best in the SMS context. This can give hints on optimized spam detection for mobile text messages.
There are several classifiers for this spam filtering, but we're only going to work on a few. And to get us started, we already downloaded off the internet the spam collection datasets. So we'll just get started with the dataset now. Instead of retrieving the dataset, we just added the datasets, and we're just going to drag it over to this end here. And to make sure that it's working well, we're just going to run that dataset, and it's working perfectly. The attributes need to be changed at this point in time because the first attribute is actually a message, and the other attribute here is actually the kind of message that's there. So those are not supposed to be that way. They need to be like unique attributes. So we need to go back to our design where we were. So just go back to the design. And the first thing that we need to do is to start by validating that. So the first thing we are going to do is we're going to use the set role operator, which is the role of the attribute described how other operators handle this attribute. This is why we're using the set role operator, because we want to make it unique how other attributes or other operators handle this attribute. So basically, since we're predicting between ham and spam, that's the attribute that we're working on. So we're just going to click ham, and we're going to set it down to a label. And just as proof of concept, we're also going to change the message, which was this one, to a regular. We're going to leave it as that, and then we're going to apply the filter. That just makes the label a bit more unique, meaning that other operators know that we're working on that particular label. So if we actually play this, you can see that this is all highlighted. So we're just going to go back to the design again. Our next operator is the rename operator. The rename operator will make the attributes a bit more unique, since now it seems like they're not as unique as they should be. We want to make it unique so that we can differentiate on what data we're actually working on. So the old name of the first attribute was ham, but we can set that up to be a message type. And the second one was this long message here, and this can actually just be a message because it's the message details. So it makes sense to us to actually label them that way. So we just apply that filter and see if they're actually working now. So as you can see, the attributes have changed to message type and message. So that's the first attribute change or validation methods that we're using, or cleaning methods on our data, so that we make things a little more unique. And since this is a supervised data set, it has all the attributes. It's not missing any attributes, so we don't need to worry about putting in attributes or filtering any attributes that are missing. So we'll go back to our design. The third thing we need to do is to select our attributes. We want to select our attributes because we need to know that these are the attributes that we're actually working on, which is the message type and the actual message. So we're going to use a subset, select the attributes. We're going to use both of these, and we're just going to these are going to be the ones that we're working on, which is the message type and the message. So we're just going to apply that. Now that the cleaning method is completely done, it's time to start applying our classifiers. There are several classifiers that have been proven to show or yield different results. So we're going to work on all these classifiers, or just 4 to 5 of them, because there are over 10 classifiers. So this is just for us to see which ones actually work better than which ones. So to do this, and so that it shouldn't be as messy, we're just going to use the multiply operator. So what this operator does is, so the rapid minor multiply operator creates copies of a rapid minor object. The operator takes the rapid minor object from the input port and delivers copies of it to the output port. So since we're using different classifiers, this is going to be quite an important part of our project. So just drag that right in there. So the example port will be connected to the input port, and now it has output ports that can go to different classifiers. Our first classifier, the one that we're going to work on, is the naive Bayes. The naive Bayes classifier has been proven to yield better results than most of the classifiers that have actually worked on the spam collection database or the dataset. So to use this as a training and testing dataset, we use the cross-validation operator. So what this cross-validation operator does is it performs a cross-validation to estimate the statistical performance of a learning model. So I'm just going to drag that in there and try and move everything over the side so that we can see everything that's going on. And then since this is creates a training and testing database, we double click on it and we're into the subprocess. In the subprocess, that's where we apply our classifier, which is the naive Bayes classifier, as we spoke about earlier. So I put the naive Bayes classifier, the training sets, to the training port there, and the mode to the mode there, and then we have to apply that model in the testing section. So we use the apply model operator, which applies a model on the example set. Our example set was the one that we're using right about now, which is the spam collection data set. So we just connect everything appropriately. So the testing set to the unlabeled port, and the most important thing is, since we're measuring the performance of different classifiers, we need to use the performance operator. We're not going to use the performance classification or binomial classification operator, even though we could use it, but we just want to make sure that by default we've chosen the right performance operator that's out there. So we're just going to connect this there, and then we're going to use the performance. We're going to connect the performance to the performance port there, and we'll go back to the process and make sure that our performance operator is connected to the results so that we see what kind of results can be found there. So we're just gonna click play. According to this, we've yielded 89.65 accuracy, which is really good for the type of classification, but we're not sure if this is the best classification. We can't know for sure until we actually put in different classifiers. So we're just gonna go back to our design and try a different classifier. I'm just going to copy and paste this cross-validation because we're going to pretty much use the same method, only different classifiers. I'm just going to connect the example to the output port and the performance here, and then we're just going to change the classifier that we're using. So we use the naive Bayes. Now the classifier that we can use is the decision tree. The decision tree is an operator that generates a decision tree which can be used for classification and regression. This is intended to create a decision on values, affiliation to a class, or an estimate of a numerical target value. So we're going to just connect those. Now going back to the process. Now using this, we can compare the two. Another interesting operator that we found during our projects research was the collect operator. The collect operator will be able to collect both methodologies. So what the collect operator does is it collects or combines multiple input objects into a single collection. That way things don't get messy. So we can remove those two there, and we can put our collect operator right there. And using our performance, we can connect both of these performance operators to the inputs, and we can connect this port down to this one, so everything can be down in one column, so everything has been collected in one so that things don't get too messy. And then when we play it, we can easily compare. So as we can see, that's performance 1, performance 2. Performance 1 was for the naive Bayes, and performance 2 was for the decision tree. Performance 2 is yielding 86.56 accuracy, while the naive Bayes was yielding 89.47 accuracy. So we can see a sudden drop in accuracy all of the sudden because of the different classifiers that are out there. The next operator that we could use, or classifier that we could use, is also based on the classification models of machine learning. The k-nearest neighbor is an operator that generates k-nearest neighbor modes, which is used for classification and regression. This is used on comparing an unknown example with a k-training example, which are the nearest neighbors of the unknown example. So we're just going to use that too. So I'm just going to copy and paste the whole cross-validation, and we're going to connect these ports as we did earlier on, and the performance is going to be connected to the collection so that it doesn't become too messy. And then we can see all our results in one pen. And then we're going to change the decision tree. We're just going to delete it, and we're going to put the k-nearest neighbor operator in there, and we'll be able to connect to the ports appropriately as they should be. And when we run this process, now we have 3 comparisons of classifiers that we can compare from. So we have the first one, which is 89.43%, which is the naive Bayes, and then we've got the decision tree at 86.56, and then we've got the k-nearest, which is at 83. So all these are in order. As you can see, the performance of accuracy is dropping down tremendously there, but we can still try other datasets that can yield different results based on these classifiers. But as for the spam dataset, this is the results that are actually out there based on the classifiers. We can try another classifier. Another classifier that we actually could work on is the ID3, which is another form of the decision tree. The ID3 is an operator that learns an unpruned decision tree from nominal data, the one that we have for classification. This decision tree learner works similar to Quinlan's ID3s. The only issue that we would have with ID3 is that if we had a lot of data, it's going to take a long time for that data to process because it uses an unpruned decision tree from that nominal data. So we're just going to copy the cross-validation again for the last time. Just this whole research group project is just for verification, just to see if all the research has been proved right, like which classifier works better than which one. I'm going to connect that there. Since we already used the k nearest neighbor, I'm just going to delete it, and we're going to put the ID3, which uses the pruned and pruned decision tree. I'm going to connect that, and as I said earlier on, if we have a large data set, it's going to take forever. So that since this has 5,000 or more records, we're just going to filter those records by range. So we use the filter operator. And we're going to filter that to range from the first example from 1000, which is a lower bound, to 2000, so that it doesn't take a very long time. So if we go back to our process, we're just going to run that again, just to see the performance. So as I said earlier, since it's a large data set and it's an unpruned decision tree for more validation, it's going to take a little bit longer than the other three classification methods that we used earlier on. So it's just going to take a bit more time than expected. So briefly, what the spam collection database does is that it just simply demarcates between spam and ham and the precision that we can get from there. So it's all done now. So we've got an accuracy of 87.24%, which isn't that bad at all compared to the other classifiers. This one was at 82.61, which was the k nearest neighbor. This one was at 86.56, which was a decision tree, and the highest, as proven by most research, was the naive Bayes operator. So thank you very much. This is the end of our presentation for the Predictive Analytics Group project. Hope to see you soon.